Hey, everybody. Happy Thursday to you. We are going to take a look at the last new thing that we're going to take a look at this year, and that is hyperbolas, the third of the conic sections that we're doing in this class. Actually, I suppose the fourth. Parabolas are also conic sections, and we spent a lot of time on those earlier in the year. But in this chapter, we've focused on circles, ellipses, and hyperbolas. And as I say it, the pun of focusing on ellipses was unintended. A hyperbola is a conic section. And here's a little bit of an illustration of that. If I've got these two cones that are meeting together at their vertex, and then this plane is slicing them in half in such a way that is um, I guess parallel to the height of the cones, but doesn't go through the center. This shape, this curved shape, is part of a hyperbola. These go on indefinitely in both directions. Um, and also, if you set a flashlight down that has a conical, I guess, path of light on a flat surface, the shape that makes on that flat surface is a hyperbola. And if you're looking at this thinking that this shape looks parabolic instead of hyperbolic, um, you're not wrong. It's very similar, but parabolas are different from hyperbolas. And the big difference is going to be that a hyperbola has something called an asymptote, or actually, it's got two asymptotes. And we'll take a look at that in just a moment. Um, Hyperbolas show up in a lot of different places, but one of the places that I thought I would highlight right now is that if you have, well, maybe you know this, the paths of planets around the sun are not circular, they're actually elliptical, caused by the gravity of the planets and the sun and all that stuff. And if you have something that passes by a planet but is not orbiting the planet, the path turns out to be hyperbolic. And as we see here, and this is actually something that when when you send something out into space, you can use the gravity of a planet to do like a slingshot effect, where if I go close enough to a planet, not to run into it, but to go by it and not go into orbit, the path ends up looking like this, and that path is also hyperbolic. Um, and if you think about as it gets farther and farther and farther away, there's a lot of curvature to the path as we're close to the planet, and the farther away we get, the less and less and less curvature there is until it looks like it's going in a straight line. And that's actually getting us close to the direction of talking about what an asymptote is. My definition of a hyperbola is similar to the definition of an ellipse. It's the set of all points where the difference of the distances to the focal points is a constant. For the ellipse, the sum of those distances was a constant, and that was something that you saw in your notes on Tuesday. Maybe you tried out the string where you put 2 points of a string down and then you can trace around with a pen or a pencil. Um, this one's a little bit more difficult to see. I'll try to illustrate what I mean by this on the next slide, but keep this in mind. The difference of the distance to the focal points is a constant. So this has a little bit of a crazy look to it, but I've got these 2 points, the point on the left, the point on the right, that are some distance apart. In the case of what we're looking at right now, they're a distance of 13 units apart. And so I'm going to say that there is a hyperbola such that the difference between the distances to these 2 points is some constant value. And to have this match up with my next slide, I'm going to have to say that that constant value, well, I'm going to start with this point. I'm going to say if I want my hyperbola to go through that point right there, the difference in the distances to these 2 points, well, it's a distance of 2 units away from the point on the left, and it's a distance of 11 from the point on the right. So this distance is 2, this distance is 11. The difference between those distances is 11 minus 2 is 9. And so if I graph all of the points on this diagram where the difference between the distances to the focal points is 9, we are going to see this thing called a hyperbola. So to find the next point, I'm going to go, let's see, if I count 1, 2, 3 units up here on this circle, but if I stay here, the distance to this point would be 3, and the distance to this point would still be the same, 11. And so the difference between them is switched. So I actually need to go up to this point right here, where this distance is 3, and this distance is 12. And 12 minus 3 gives us that same 9 that we got when we did 11 minus 2. And then the mirror image of that point is down here on this side. And then I've got a few other points that I can put on here. This one is a distance of 4 away from the point on the left, and a distance of, this must be 13 from the point on the right. 13 minus 4 gives us that same 9. That matches up with that point. And this would keep going up in this direction. You kind of see the pattern of what it looks like. And then the mirror image over on this side is going to look the same, where I'll have these points connected, and I've got them all on the next slide. So I'll just draw this. And then when we finally connect those points, we see the shape. This is the shape of a hyperbola, which is definitely unique and different, but that is what a hyperbola looks like, or that's one way that a hyperbola can look. Now, if I had chosen a different value, if these were a different distance away from each other, if I chose a different constant value, we would have some different shaped hyperbolas, but they would all have this feature in common. I'm actually going to draw something on this graph. There's a line that goes this way and then another line that goes that way. And these lines are something that are called asymptotes. And I don't know if we've seen that phrase in this class. I'm trying to remember if I've used that phrase in this class. I think I used the phrase asymptote when I was talking about translation of functions. In fact, now that I think about it, I do believe I put my magnet on the board with the phrase asymptote in it. But an asymptote has the property that as we move farther and farther off into the distance, the behavior of this graph is getting closer and closer and closer to the behavior of that asymptote. Right here, we see a lot of curvature to the graph, but as we get farther and farther and farther away, it behaves more and more and more like this line. Now, sometimes we have hyperbolas that have this shape, and we just saw the shape here where it opens. I'll refer to this as opening to the left or to the right. So we've got a shape that looks like this. And then I'm about to put the equation on here so you can take a look at that also. And it's going to have, actually, I'll just draw it up here. Why not? X squared over a squared minus y squared over b squared equals 1. And this looks very similar to the equation for an ellipse. In fact, the only difference is that instead of a plus, we've got a minus in between the two. But this a, got a squared as the denominator. This distance a is a distance to the center of my vertex. And then this distance b, that's a vertical distance corresponding with the y value. That distance b is this vertical distance. And what I'm doing is I'm forming this rectangle. We'll take a look at this again later on. But in this rectangle that has a width of 2a and a height of 2b, the asymptotes of this hyperbola go through the corners of that rectangle, both positive slope and negative slope. And so as I'm drawing my hyperbola, the hyperbola will pass through these 2 points that are vertices of the hyperbola, and then will approach, as we get farther and farther away, it will approach these asymptotes that are slanted. And then there's another possibility for a hyperbola that is a hyperbola that I will refer to as opening up and down, the top and bottom. Now I'm actually going to just copy and paste what I drew or what I wrote here. I will have to change it slightly. And the change that I'm going to have to make is switching my x and my y values. If I have an equation that is, this form, where the y value comes first, That's what's going to make this thing open up and down instead of left and right. And if we think about plugging values into this equation, it makes sense that the term that is positive ends up being the direction that we go to get to the vertex. If y is the first term, we're going to go up and down to get to the vertices. When x was the first term, we're going to the left and right to get to the vertices. But then the rest of this is the same. A is determining your vertical because it's associated with the y value. B is determining our horizontal distances because it's associated with the x value. And then when I've got those distances A and B drawn, I draw the rectangle around those. And by the way, all these dotted lines, these are not a part of the actual hyperbola. The only part of the actual hyperbola is this curve up here and this curve down here. The curves go through the vertices, both above and below, and approach the asymptotes. The farther away we get, the more the behavior acts like that of the asymptote. And I think I may have stolen my own thunder by doing that all on one slide, but that's the basics of what these look like. X squared over a squared minus y squared over b squared equals 1, or switch the x and y values, and the only thing that that does is switching where your vertices are and whether it's opening up and down or opening to the left or to the right. Um, the A and B, I've taught hyperbolas in different ways. I've taught it in such a way where the A always stays with the x value. So the A would be here and the B would be there. And there's just lots of different ways of thinking about this. Whichever one is associated with the x is giving you horizontal, whichever one's associated with the y is giving you vertical, no matter the order that things are in. And that's always going to be the case. So when we're graphing these things, when we drew an ellipse, and this is what we did earlier in the week, we found where the center was, and then we found some distance, the horizontal distance, whatever that was. So I'm going to say that this horizontal distance was 2. So we had, I suppose, a 2 squared or a 4 in the denominator of the x term. And then I'll go up and down 3. So the denominator of the y term was a 9. And then we just connect the dots with those. And we draw an ellipse like that. When I draw a hyperbola, it's going to be almost the same thing. I'm going to do the same process. I find the center, I count off to the left, I count off to the right, I count up, and I count down. And so far, everything is the same as when I drew an ellipse. But now, instead of just playing connect the dots and drawing my ellipse, I'm going to imagine the rectangle that has these 4 points in it. So I'm going to put the corners of my rectangle down here. And then I'm going to draw a dotted line showing the asymptotes. And if I was doing this on paper, I would actually use a ruler to make these lines more straight. And so far, everything that I've drawn has just been helping me out in actually drawing the hyperbola. And now, if this is an x squared minus y squared situation, the 2 points that are horizontal would be my vertices. If this is a y squared minus x squared situation, then the points on the top and bottom would be vertices. So it depends which type of a hyperbola we've got, but one type goes through this vertex. It's vertical just for a moment, and then it levels off and approaches that asymptote. Or here, starting vertical and leveling off and approaching the asymptote that way. And then the same kind of thing happening over on this side, approaching that asymptote, or going down in this direction and eventually approaching the asymptote in that direction. That's what drawing hyperbolas is going to be like. I don't want this lesson to get to be too long, and so I debated with myself. On your homework assignment, it looks similar to the ellipses assignment, where there's a page of kind of walking through the process, and I'm going to choose to let you walk through that on your own. I think you'll probably be able to figure it out pretty easily, just following the directions, comparing with what you did for ellipses. But I wanted to make sure that we saw some actual graphing of hyperbolas. I feel like that's the more challenging part of this, and the part that I want to go through with you in this lesson. So I'm going to do a couple of examples. The first one I want to take a look at is an x term first, so x squared minus y squared as the form. And I'm going to start by looking at this part. I've got an x minus 1, I've got a y plus 2. That's determining what my center is. I've got x minus the x value and y minus the y value. We've certainly seen a lot of this. Y minus -2 is the same as y plus 2. So my center is at the point 1, -2, right there. And then I'm going to look at the 36. Of course, that's 6 squared. This is the coefficient associated with the x term. So this is telling me the horizontal distance from my center to the edge is going to be 6. The square root of 36 is 6. So I'll count off 1, 2, 3, 4, 5, 6 horizontally. 1, 2, 3, 4, 5, 6 horizontally. Again, horizontally because this is going along with the x term. And then vertically, with the y term, I've got 64, 8 squared in the denominator. So from the center, because it's associated with the y term, I'll count up 1, 2, 3, 4, 5, 6, 7, 8, and down 1, 2, 3, 4, 5, 6, 7, 8, all the way down to the edge of my graph paper. And so now which of these are vertices and which of these are covertices, again, is determined by what comes first. I have an x coming first, x squared minus y squared form, which means my hyperbola is going to be opening to the left and to the right, which means these points are my vertices. My vertices are at, oops, let's continue with the color coding. One vertex over here is at negative, let's see, if I count it off by 6, this must be -5, -2. And then the other one is 6 more than 1, so 7, -2. So those two are my vertices. My asymptotes, well, I'm going to keep going with my drawing here. So I know I'm going to the left and right by 6. I'm going up and down by 8. And so if I find the point up here that's going to finish off my rectangle, up 8 and over 6 and down 8 and over 6, up 8 and over 6. Let's see, I must have a dotted line tool over here somewhere. You're going to use a ruler as you do this. I'm going to use the tools that I have with my software. There's one asymptote that goes that way and another asymptote that goes that way. And if you want to draw the rectangle on there, you can draw the rectangle. You don't need the rectangle drawn, but some people like to see that. Now the equations for these asymptotes, oops, there's my pen. I'm going to go with the point slope form of a line and say that this point right here, both of these asymptotes go through the point 1, -2. And so in point slope form, since the y value of my center is at -2, I'm going to go with y plus 2, y minus the y value equals the slope. Now the slopes of these lines, this line goes up 8 and over 6. This one goes down 8 and over 6 to the right by 6. So these two lines have opposite slopes. We've got both positive and negative slopes depending on which one we're looking at. And these slopes are, I repeat, up 8 over 6, rise over run. I'm going up and to the right, so it's a positive slope. 8 divided by 6, I'm going to call that 4/3 for that slope. And then y minus the y value equals the slope times x minus the x value. The x value of that point is 1. Also notice this, I've got the y plus 2 here, I've got the y plus 2 there, x minus 1 there, x minus 1 there. Definitely some similarities. And then I think all I have left to do is to actually draw the graph. I've got a vertex here. I need to approach this vertical asymptote. So it starts going straight up, but then as I get closer to the asymptote, it approaches that value. Its slope or the weight that it's changing is more and more and more similar to that asymptote. Same thing, oops, over on the other side, goes straight up, but then approaches the asymptote in that direction. Same thing here. Starts straight down and then approaches the asymptote down in that direction. And as I'm looking at this, I think, yeah, I just inadvertently did one of your homework problems for you, but that's okay. As long as you're following along and if this is making sense, then that is all that really matters. This next one that I want to do is not the same. I'm just going to double check and make sure. Yes, I am not doing a homework problem for you here, but I would like to do another one. If everything has made perfect sense, then go ahead, by all means, stop this video and go ahead and walk through the homework assignment, but I will do one more example for those of you that would like to see it. The big distinction here is that I've switched the x and y terms. Instead of the x term coming before the y term, my y term's coming before the x term. But as long as I've been thinking about things correctly, that shouldn't be a big adjustment. My center, I've got x minus the x value. Again, I'm looking at x before y. Here I've got y plus 4, that is y minus negative 4. So my y value is negative 4, no problem there. 1, 2, 3, down 1, 2, 3, 4. There is my center. I will take a look at my vertical. I'm going to start with my y term, my vertical. The denominator is 25, which is 5 squared. So I'll count up 1, 2, 3, 4, 5. Again, because I'm looking at the y term, I'm thinking vertically 1, 2, 3, 4, 5 from the center. And then when I go to the x term, my denominator is 49, so I'll count off 7, the square root of 49. 1, 2, 3, 4, 5, 6, 7, all the way to the edge of my graph paper. 2, 3, 4, right there. And so those distances, the horizontal, because it's associated with x, those are determining the size of my rectangle, the shape of my rectangle. My vertices, because this is a y first equation, y squared minus x squared form, that means that my vertices are the vertical points. And so I suppose I just found those. Let's stick with my color coding. Let's see, this one I've gone over 3 and up 1. So I've got a vertex at 3, 1, and then the other one is at 3, let's see, down 4, and then another 5 after that, so down 9. So 3, negative 9, those are my vertices. To draw my asymptotes, I'm going to finish drawing the corners of my rectangle. Again, straight up and straight down from the points that I already found for the vertices. I am going to switch over to my dotted line. So there is one asymptote. And the second asymptote, missed my target there, looks good right about there. I suppose I should write down the equation for those asymptotes. Again, y minus the y value of my center. My center's at negative 4, so y minus negative 4 equals, I've got both a positive and a negative slope. Let's see, we're going up by 5 and over by 7, so my slope is either positive or negative 5/7. And x minus the x value, my x value is 3, so x minus 3. Again, notice that I've got an x minus 3 here that showed up in the equation, a y plus 4 that shows up in the equation also. So those are the equations of my asymptotes, and all I have left to do is to draw my curve. The points, the vertices are on the top and bottom this time, so it starts off horizontal, but then approaches as I get farther away, approaches the asymptotes. Same thing over on the left side and also on the bottom. Starts off horizontal. It's got a horizontal tangent line, but then as I get farther and farther away, it approaches the behavior of the asymptotes going in both directions. Okay, there we go. That's definitely enough for today. Make your way through the homework assignment. That'll also be a little bit instructive today. And we'll have our last day of instruction tomorrow. So have a great day. Hopefully you're doing all right. If not, let me know what I can do to help you out. Otherwise, I'll see you later. Bye-bye.